So today's video is going to be using the disk method. We're doing revolution of surfaces using the disk method. The disk method is how we're going to find volume today. All right, so I'm going to call this one the wedding band example. All right, it's going to be the wedding band example, and you'll see why when I put it on the computer screen. All right, so we're going to find the volume of a wedding band, all right, by rotating the graphs. F of x is equal to 4 minus x squared, and g of x is equal to x squared plus 2 about the y-axis. All right, so these two equations are going to be your important pieces of information, plus knowing which axis we're about to revolve around. All right, a note before we get started. Integrate the area will yield volume. All right, integrate the area will yield volume. Believe it or not, what you're looking at right now is the wedding band. All right, so it looks like a football or something, right? But it is a wedding band, and you'll see why in a second. But I'm going to go into the two functions. The one on the top, the one that's going like this, that one is the 4 minus the x squared, and I'm starting at a -1, then I go all the way and I stop at +1. Now, the part at the bottom, that's the one that's up here, right here at the bottom. That one is my x squared plus 2, and it's the same thing. We're starting at -1, and we're stopping at +1. So that gets my outer surfaces drawn. So now I have my outer surfaces ready. So if I were to take a vertical drop, right, and then I just connected the top surface to the bottom surface, I create this little slice that has to stay inside of my wedding band. And believe it or not, it's this slice that is going to get us to the volume. The slice gets us to the volume. All right. So there's a reason why we call it a disk method. I'm not going to really talk about it right now on the whiteboard. It'll make way more sense when you see it on the computer. But what I will do is show you how to set up the integral so that you can get the volume. So if we were to continue from what we talked about yesterday, remember yesterday we took the radius and then we spin it around and we spin it around. That's literally what we're going to do today. But remember, we're talking about two surfaces. We got one at the top and the bottom, and the whole thing has to spin around. So this slice is important because we can only know what this slice is by subtracting these two. All right. You know what this one is if you take the longest one and you take away the shorter one. And when you do that, it gets rid of this and it leaves you with that. All right. So that's what I'm going to write on paper first. And then from there, we're going to figure out the volume. So to put that in layman's term, just in regular English, basically you take the big radius, you subtract the small radius. Big R minus little r equals the slice that you need to get your disk. All right. So remember, if I have a circle, I know the area here is pi r squared, all right? Now, what happens when I have another circle around it and I'm just want to figure out that ring? You get what I'm saying? It's a ring there. So what happens is now I have a big R. Now I have a big R minus the little r. Because when I subtract this small one, it's going to leave me with the rest. All right. So the area of a circle is pi r squared. But when I say the area of a disk is pi, and it's the big R squared minus the little r squared. You get what I'm saying? So it's still like pi r squared, but you have to do a pi r big R squared minus the little r squared. And then all right, so here's my equation that's going to give me the volume of the wedding band. So there's my volume. There's my pi, big R squared, right? That's my big R squared. And that's my little r squared. And I am subtracting the two. So I have pi. And remember, I start at -1 and I go all the way to +1. And that's going to give me the volume of the wedding band. So I'm about to go to the computer screen so that you can see the wedding band, so that you can see the disk and all of that. All right, so we're going to look at this in 2 dimensions right now. So there's my top curve, there's my bottom curve, so there's my two surfaces. And remember, I had a slice right here that can move back and forth. There's the slice right there. So that's what it looks like in 2 dimensions. And I don't know if you can see them at the same time. So on my left is 2 dimensions. The screen right there on the right is 3 dimensions. And notice how they do correspond to each other. Now, what I'm about to do is I want you all to look at that slice that's moving back and forth. So I am going to spin that one. So when I spin that one, look what happens. See that? Once I spin it, now you see why we call that a disc. Because it's stuck inside of the two surfaces. And when you look at it straight on, it looks just like a disc. When you look at it straight on, it looks like a disc. And when you move it back and forth, you'll see that the disc changes size. Depending on where it's at within the two surfaces, it may get a little wide and it might get extremely thin. But it is a disc. So that's why we call this a disc method, because what's going on inside of the surfaces is a disc. And it's the disc that we can figure out the areas for. And remember, once you stack all of those areas, you'll know the volume. All right, so I'm gonna get that all the way to the end. And then now what I'm about to do is spin both surfaces. And whoop, there it is. And that's what we mean by like the wedding band. And that's how it looks. And maybe, let's see, let me spin the disc around. I don't know if you can see the disc inside of it. Yeah, I think you can. You can see the disc inside of it. See that ring right there on the inside? See how you can see it go from end to end on the inside of the surfaces? That's what we use to calculate the volume right there. Is that disc. Every time we move it, we log its area until it gets all the way to the other side. And whatever that number is going to be the volume of the surface. There it is. And if that didn't look like a wedding band to you, it's only because I didn't adjust the numbers on the screen. So I can adjust it so that it doesn't, I could stretch it if I wanted to or make it thin just like a wedding band. So it just all depends. So yeah, it is still, we call that the wedding band example. But if it didn't look like one, it's only because the numbers weren't pulled a certain way so that it looked like a ring. That's all. And there it is. Got rid of the axis so that it just spins by itself. And there it is. So I'm not going to go through all the steps that it takes to find the area, but what I did want you all to see was how to set up the equation that will give you the area. And there it is. Wedding band. All right, so the software that I'm using is called Geogebra. I use Geogebra 5, which is an older version. It does everything I need it to do, but I do like using this software for pretty much all of my visual demonstrations and stuff. So you can download that for free. They even have the apps that you can use on the phone. They let you use augmented reality. You can actually stand up and walk around things that you design, and you can go inside of them and all sorts of stuff. So I might do a video on one of those later. But that's the software that I'm using. And don't forget to check out my YouTube channel.